Welcome back to ECE 501B. Homework number 4 was just posted, and it's due on the 20th, which is a few days away, if today's the 3rd. And it deals with eigenvalues and eigenvectors, and hopefully the solutions, maybe they won't be available right at 5:30, but we'll see if we can make them appear sometime, maybe this evening, to let you see the solutions if you don't already know those by heart after taking the exam. Today what I want to do is start back up on Chapter 5, which is Eigenvalues and Eigenvectors. We will recap the 3 examples that we talked about before the first exam, and then we will look at an example where we actually have a matrix with real elements that doesn't contain eigenvalues that are real. And then that will lead us into a more general discussion of invariant subspaces, particular facts about invariant subspaces. And invariant subspaces, just be thinking about it doesn't change. So it's a subspace, and if we use an operator on that subspace, if that subspace is invariant, then that operator maps us back into that same subspace. The subspace is invariant. And we'll look at some different invariant subspaces, but you already know some of those. The null space is an invariant subspace. The range space is an invariant subspace. And obviously the entire vector space is an invariant subspace. Then we will look at definitions of eigenvalues and eigenvectors, and I may post some additional material on finding, or a method for finding, eigenvalues and eigenvectors in general. We'll look at some of those processes in today's class, but we won't talk about it necessarily in general. To recap what we have talked about already, is now we're dealing with an operator, which means that we're going from a vector space back into that same vector space, meaning we're going from V to V. And if we're talking about eigenvalues and eigenvectors, those need to satisfy this equation. The operator applied to a vector is equal to a scaled version of that vector, V, where the scaling is the eigenvalue and the vector we call an eigenvector. Last time we looked at 3 particular matrices, one that was diagonal, one that was upper triangular, and one that was dense, or didn't have a lot of sparsity. There were not a lot of empty spaces in the matrix. And in each of those 3 matrices that are 2 by 2, they all 3 had exactly the same eigenvalues, -1 and -2. But the distinction then comes in the eigenvectors, and I've obviously not carried out the significant figures on the eigenvectors very much, but I'm just trying to show or illustrate that they are different between the 3 different matrices that we started with. The eigenvalues associated with the diagonal are right there on the diagonal, as the same with an upper triangular or a lower triangular. The eigenvectors of a diagonal are basically the standard basis vectors, can be chosen as eigenvectors. When we have upper triangular or lower triangular, then we get a little bit more interesting pattern or structure in our eigenvectors, and we get much more interesting patterns in our eigenvectors when we are dealing with dense or non-sparse matrices. What we want to do today, to start with, is our 4th example, and this example is illustrating the fact that we can start with a matrix, a 2 by 2 matrix with real elements, but yet it does not have real eigenvalues. let's say now that we have C for complex, but it's not complex in terms of its entries in the 4 elements of this 2 by 2 matrix. What we want to do is now try to find what particular values, lambda, might satisfy our eigenvalue-eigenvector relationship, and what eigenvectors might satisfy that. Let's then look at the eigenvalue eigenvector equation. And this you need to essentially have memorized. Somebody asked about whether or not the material on the final would be cumulative or comprehensive before class, and I said, even if it wasn't, it is, if that makes any sense. Because everything that we have learned up to this point, you have to know in order to keep going in the class. So it is definitely cumulative, the material, and I could ask you a question at the end of the class that essentially utilizes all the information prior to that topic being covered in class. So just as a heads up, yes, the final, let's agree, is comprehensive or cumulative. But with this eigenvalue-eigenvector equation, we can now rewrite that as C minus lambda I x equaling 0. Or you could have done the negative of that. We could take everything on the other side, and we could have lambda I minus C times x equals 0, and that also would be true. A lot of times it's easier to think of the lambda I and subtract the original matrix. Let's then use the second relationship, which is consistent with the first relationship. But now for the particular matrix C that we started with, we had minus 1 on the diagonals. And so when we subtract a minus 1, we end up with lambda plus 1 and lambda plus 1. And now we're negating the off-diagonal terms, and we had a 2 in the 1, 2 entry and a minus 2 in the 2, 1 entry, and that's now our lambda I minus C matrix. That now is multiplied by a 2-dimensional vector x sub 1 and x sub 2, and we want those values of lambda and x's to produce a 0 vector. And really, this eigenvector is living in the null space of that matrix, lambda I minus C. That's the definition of null space, is that it maps us to the 0 vector. If we look at the 2 equations that arise or result from this matrix relationship, we can then write down that we have lambda plus 1 times x1 minus 2 times x sub 2 is equal to 1. And we can now write down for the second equation, we have 2 x1 plus lambda plus 1 x sub 2 equaling 0. We have 2 equations. Let's say that we have some value lambda that we want to eventually find, but right now let's just assume it's constant. Then our 2 unknowns right now are x1 and x2. Let's use this second one to actually solve for x1, where now x1, if we divide by 2 and take the other term to the other side, we have x1 as minus 1/2 lambda plus 1 x sub 2. And what we want to do now, actually, is take this x1, put it back into the first equation, eliminating x1, and we will end up with one equation in the one unknown x sub 2, assuming that lambda is a known quantity or yet to be determined value. But we're not treating it as an unknown just yet. So that now we have minus 1/2 lambda plus 1 times lambda plus 1 x sub 2, replacing x1 with what we just found, then minus 2x sub 2 is equal to 0. Or if we multiply all the terms by minus 2, then we end up with lambda plus 1 squared x sub 2 plus 4x sub 2 equaling 0. We have an x sub 2 in common with those, so let's factor that out. And we now want lambda plus 1 squared plus 4, that quantity times x sub 2 equal to 0. We're now trying to find a solution to that equation by maybe making the bracketed term become 0. Because we really want x1 and x2 to be non-trivial. We don't want to set those elements equal to 0. So we're forcing x2 and x1 to be something other than 0. And we're interested in the question, is there a real value for lambda? Is there a lambda that's real such that lambda plus 1 squared plus 4 is equal to 0? Is it possible to solve that equation for a real number lambda? No, there isn't. Lambda now can take on real values all day long, and if we let it equal to what lambda would minimize that expression or get it as close to 0 as possible. So if we let it equal 0, we have 5 on the left. Is there another value of lambda that might make it smaller than 5? -1 would eliminate that squared term, and we have 4. So we can only get down as low as 4 in trying to approach 0 with real values of lambda. The answer then is no, there's no real value of lambda. Lambda plus 1 squared plus 4 is always greater than or equal to 4 and greater than 0 for real values of lambda. And we could sketch that. That's a quadratic function of lambda. You just told me that the minimum was at -1, and so this probably won't be very to scale, but there's 4, and now this is going up for all values of lambda on either side of lambda equal -1 in this quadratic structure or in this quadratic shape. Which means that there's no real values of lambda that satisfy our eigenvalue-eigenvector equation. That's where these two equations came from. If we open it up a little bit and try to find other values of lambda that might cause that to vanish, meaning if we let those scalars be in the complex number field, then we're going to be in better shape. Let's then find the roots of lambda plus 1 squared plus 4 equaling 0. Or adding -4 to both sides. If we now take the square root of both sides, the square root of a minus number introduces this square root of -1, which we can represent, let's just do it as j. And with the square root, we get 2 roots, and the square root of 4 is 2. And now we have something that's getting us close to finding the roots that we wanted. We now can say that lambda is equal to -1 plus and minus j 2, and that's actually an element of the complex field, C. And we've now demonstrated then that this original matrix C that started with real elements, minus 1, 2, minus 2, minus 1, has no real eigenvalues, but I do want you to maybe pay attention to the eigenvalues that it had and the structure of C itself. C was actually written in a form where the real part was on the diagonal and the imaginary pieces were in the off diagonal. You can now see that we have minus 1 plus and minus j2 staring at us in that particular representation of C. And if you have something like that, any submatrix within a matrix, you can now essentially state, oh, my eigenvalues are complex. They have imaginary parts, and they will be real parts of minus 1, and then we have a sign change among the two off-diagonal terms, and so we now have plus and minus j2. That's really sort of a standard way of writing complex eigenvalues in a 2 by 2 real matrix form. We've now looked at examples: diagonal, upper triangular, it could have been lower triangular, dense or non-sparse, and now we have one that has non-real eigenvalues. Let's start to formalize this study a little bit of eigenvalues and eigenvectors. And now we are in a particular category of linear maps, and in particular, we're dealing with operators. And remind me again what an operator means. If we start throwing this word around, operator, you need to immediately start thinking in what way. So now our input vector space and our output vector space are the same. If we have an operator, then that's what we're implying. We're saying that the input vector space is getting mapped back into itself, and that might be, let's say, V. Let's assume in this study of operators, V is always a non-zero finite dimensional vector space over one of our fields, R or C. And that's actually the heart of this course. And we're trying to really understand the structure of linear operators which we can, in equation form, say these linear maps T are now an element of script L of V, where now that is implying that we're going from V back into V. The input vector space is V, and the output vector space is V, and that's now an operator. The linear map is now an operator. A useful place to start this discussion of operators is by considering our vector space as having a direct sum decomposition. What do we mean by that? Or how could we then write V? If V is our vector space and now we want to have a direct sum decomposition, what was the notation that we used for that? We had a plus sign with a circle around it, didn't we? And now we really, these subspaces that we're decomposing our vector space in do not overlap. They really just intersect at the zero vector or at the origin in whatever vector space we're dealing with. Let's now say that we have decomposed this as a subspace U1, direct summed with U sub 2, etc., direct summed up to U sub n. So now we're in Nevada, and that will maybe become a little bit more informative or descriptive as we go, because we may actually start thinking about a city in Nevada in just a minute. But now we have lowercase n, and that will hopefully make sense in a little bit. Just stay tuned. So we now have this direct sum decomposition, and it's now possible to decompose any vector in our vector space V to have a unique representation among or within these subspaces U1, U2 up to U sub n. That is, every element in our vector space V has a unique decomposition in terms of elements of the various subspaces. Or every vector space. And one thing that we should sort of recall is that every vector space has a decomposition like this. Or the ability to perform a direct sum decomposition. It could be the almost trivial case where you have the direct sum of the original or the full vector space with the zero vector. Although it might be the trivial case where V is now V direct summed with the zero vector. What we want, though, from this direct sum is this property of not having overlap between the different subspaces, U1 through U sub n. Now, since we have split our original vector space V into non-overlapping subspaces, with the exception of the zero vector, of course, except for 0, or the zero vector. That's now a vector in our vector space. And the reason is that all subspaces, to be a subspace, you have to contain, or a subspace needs to contain, this additive identity, or the zero vector. We can think of this linear map T, which we've now specialized to being an operator, as acting on each of these subspaces independently. And the book actually uses a particular notation for that. And the notation is, there's our linear map, which is now a linear operator, sort of restricted to, that's what that single vertical bar means, a subspace U sub j. That's the notation then for T, the linear operator, restricted to the subspace U sub j. And that would be nice if we could always have that operator mapping from this subspace back into that subspace, but that's what we can't always guarantee. We can't always guarantee that for a generic map. Unfortunately, this restriction to a subspace isn't as helpful as we might hope. Since there is no guarantee that this operator T restricted to U sub j is an operator on U sub j. By that I mean, or that is, it might, as a linear map, it might map some vectors that start in U sub j. It may map those out of U sub j. It might map some vectors to other subspaces. And before we just keep going on and on and on about maps and different subsets, let's look at an example that hopefully might make this a little bit more clear. So that let's consider our vector space V to be R3, three-dimensional space. So now you can visualize that we're living in this room that has our standard directions. Let's say that U1 is the x-axis, that's one subspace. U sub 2 is the y-axis, that's another subspace, and U sub 3 is the z-axis. And hopefully it's clear that U1 direct summed with U2 direct summed with U sub 3 does in fact decompose the three-dimensional R3 vector space V. Since any vector in our original vector space R3, which we said was V, can be written uniquely as some vector V1, which is U plus V plus W, with U now coming from the subspace U1, or the x direction, or on the x-axis, or living in, or the x-coordinate in the 3 space. V is the component in the y direction, and W is the component in the z direction. So we now have our vector space V, and we've decomposed it into x, y, and z, the standard subspaces associated with R3. Let's now look at a particular map. Suppose we consider the following map. Let's say we have T operating on a 3-dimensional vector, and now we've labeled those x, y, and z. And suppose that x, y, and z now, when we start in 3 space, get mapped to minus y, x, z. Before I say any more or draw a picture of what this might represent, do you see what might be happening with respect to this linear map? Can you say anything about it? What happens to the, let's say, the vertical direction z coordinate through this linear map? It stays fixed, doesn't it? What happens to the x coordinate? It gets mapped to the y-axis, and what happens to the y-coordinate? It now gets shipped or mapped to the x-coordinate in the negative half of the x-coordinate, and so actually this is, in fact, a 90 degrees counterclockwise rotation in the xy plane. Where if we take the following picture, let's say this is now U1 and this is U sub 2, suppose that we start over here at x and we start here at y. Then after the mapping, we get mapped down to, whoops, minus y. T takes us there, and T takes us from x, it takes us up here to x. And there's our 90-degree rotation from this linear map, T. And we want to know, does this linear map actually, is it a good operator on all 3 of these subspaces that we've now done a direct decomposition of our underlying vector space R3 that we started with? And the answer is obviously no, or I wouldn't have picked this. But let's now consider a particular example. Suppose we consider T restricted to U sub 1, which is the x-axis. Meaning, let's just have a non-zero x-coordinate to begin with, and zeros in y and z. And where does that take us in terms of this particular linear map? Y now started at 0. That's now becoming our x-coordinate, which is 0. X bumps up to y. We now have a 3, and z didn't change. Now, as our output vector, 0, 3, 0, belong to the subspace 1, 0, 0? No. So here's a map, T, that you can start in U1 and boom, you end up out of U1. So this linear map is not an operator on U sub 1. It doesn't function as a operator on that one-dimensional subspace, capital U sub 1. T is not an operator on this subspace U sub 1. Or we could say that as what starts in U1 does not stay in U1. And now I bring us back to the n dimensions being in Nevada, meaning what happens in Vegas stays in Vegas. Now we have something that starts in U1 and it doesn't stay there. So this is not like what's supposed to happen in Las Vegas. Meaning here, we've started in U1 and we didn't stay in U1. So think Las Vegas, and maybe you'll remember that that operator concept does really depend on the linear map and your subspaces that you're decomposing your vector space into. What we want to talk about now are, in fact, subspaces that do possess these properties, and we're calling those invariant subspaces. And these subspaces are quite special. Or this idea of a restricted operator being an operator on a restricted subspace is very important. And we call a subspace where this behavior is true an invariant subspace under this linear map T. Meaning, if we're given, or that is, given a linear operator T on this vector space V and a subspace U, U a subspace of this underlying vector space V, U is invariant under T if we pick any arbitrary vector in that subspace U, and that actually implies that applying that linear map T to U keeps you in the subspace U. That is, T restricted to U is in fact an operator on the subspace U. Let's look at an example that actually doesn't involve tall, thin columns, but maybe vector spaces that are coming from a different direction, and that's with polynomials. So let's look at an example that is offered up in the textbook. And that is, suppose that our underlying vector space is the space of seventh order polynomials on the field of real numbers. And let's assume that our linear map, T, is actually the differentiation operator on P7. I think it's clear that T is an operator on the vector space V. If we start in P7 and we perform a differentiation on a seventh order polynomial, do we stay in P7? We may reduce the order, but we're still in P7, aren't we? So yes, we are reducing the order, but we're still in P7 because a sixth order, a fifth order, a third order is still in P7. So T is in fact an operator on the underlying vector space V. Now let's look at a specific subspace of V. Suppose we consider the subspace U to be the subspace of fourth order polynomials P sub 4. It should be clear that U is a subspace of V. And now let's pick a vector in capital U. What's that mean? What's the vector U? It's a polynomial that's fourth order, or it lives in P4. So it could be as big as a fourth order, it could be a second order, it could be a first order, it could be a constant. But we now have a vector U that its highest order is restricted to fourth order. What happens when we now apply this linear map, T, to that vector U? Where do we end up? If little u, a vector, is at most a fourth order polynomial, and we differentiate it, we still end up in the same place we started, don't we? We still end up in capital U, this subspace of fourth order polynomials. This now returns us to U, which means then, therefore, this subspace of fourth order polynomials is an invariant subspace of the underlying vector space P7 under that particular linear map, which was differentiation. What if we take a little bit of an aside? What is another subspace, let's call it Q, of this vector space P7 such that P7 over the field of reals is equal to P4 over the reals direct summed with Q. We're looking for a subspace now, Q, that forms a direct sum decomposition with P4. So now if we want a direct sum decomposition, what do we want? We really are trying to minimize the overlap, aren't we? Meaning we can't just say a fifth order polynomial. We do need to pick up 5, 6, and 7, don't we, in terms of powers of x, if that's what we're dealing with. But we can't pick up powers of 4, 3, 2, 1, or constants, can we? But we can define this subspace. We could define Q to be A5, let's say Z5, plus A6, Z6, plus A7, Z7, such that these coefficients, A5, A6, and A7, belong to the set of real numbers. And that would be okay. Now we have a direct sum decomposition, and the only vector in common between Q and P4 is the 0 vector. That was just sort of an aside of how we might find direct sum decompositions. Let's look at some facts. Returning now to these invariant subspace. Some facts about invariant subspaces. Suppose we're starting now with this operator T on a vector space V. So that's what we're given. One fact is that the null space of that linear map T is invariant. What does that mean? If I give you a vector x that's in the null space of T, and I apply T to that vector, what happens? You get back to 0, which is in the null, so that x stays in the null space of T. So that null space is an invariant map. The range of T is invariant. Which means now if we start in a vector that gets us somewhere in the codomain, then we're going to stay in that codomain with that vector. If we operate on that vector with the linear map T, we'll end up in that same range space of T. We'll be back in the range of T. There are some other invariant subspaces. Now you can think of two sort of trivial subspaces What's a trivial subspace of a linear map? The whole vector space V. What's another one? The zero vector. Those are sort of trivial vector spaces, or I'm sorry, subspaces that are invariant under the linear map T. Invariant subspaces other than the zero vector and V must exist if A, the dimension of our underlying vector space V is greater than or equal to 1, and our underlying field is the field of complex numbers. So we know now that we have invariant subspaces that are one-dimensional or larger. B, we can find invariant subspaces if our underlying vector space V is greater than 2, and F is R. So maybe what I could say is greater than or equal to 2. I think maybe what I'm wanting to say is greater than 1. I'm kind of wanting you to keep track of this 2, so maybe I will go ahead and say greater than or equal to 2, and F is R. But I need to double check that, and you can too. But essentially, if we have, as we illustrated earlier, with this rotation in this 2 space, if we have a complex set of eigenvalues, we're not necessarily guaranteed of getting back into or having an invariant subspace if we have essentially eigenvalues that would have to be complex, or sort of some kind of rotation in our underlying operator. Let's now look at some specific first order or one-dimensional invariant subspaces. Simplest subspaces that are in fact invariant. Or maybe I should say simplest subspaces that are, let's say, interesting. What do we mean by a one-dimensional subspace? Suppose we're given a U, let's say that it's in V, just some vector in V, and suppose that we now define a subspace U defined by any scalar multiple of that vector U. This subspace U is all scalar multiples of U. And we want to ask the question, what happens if U, in fact, is an invariant subspace? what happens if U is invariant? Suppose we take a vector W that's in U. And again, we're saying that U is invariant relative to this map T. If I now take TW, where does that live? That still is an element of U if U is an invariant subspace. Or that says that TW is in fact a scalar multiple of our original vector W. And how could we write that? We now are saying that we've taken a W that's in U, and U is invariant under that linear map T, and U, remember, as a subspace, was just defined as this one-dimensional vector little u, and we've now said that we end up back there, and the way that we end up back there is we now are some scalar multiple of W if we're back in that subspace U, where lambda is coming to us from our field of numbers. And that expression should look very familiar to what we've already been doing. But we basically derived that equation by talking about one-dimensional invariant subspaces. If we now have this relationship, what are we calling lambda? Lambda is our eigenvalue that we were defining or talking about before. We call lambda an eigenvalue, and it came into being because we assumed we had a subspace U that was one-dimensional, that was invariant under this map T. We call lambda an eigenvalue of T, our linear map, if there is a non-zero vector W such that TW equals lambda W is in fact true. And we give W also a distinct description, or a word to describe that, and that's our eigenvector. This vector W is called the eigenvector associated with that scalar lambda. Question? W is a vector that's in this subspace U, where U is a subspace in V. And we're just now saying that suppose U is invariant, and we pick a W that's in that U, then that says that if we start in U, we stay in U relative to this linear map T. And if that's the case, and U, by definition, was a scalar multiple of one vector little u, then we know that TW is in fact equal to lambda W. And we give those, if we have such an equation being true, tw equal lambda w, then w is our eigenvector and lambda is our eigenvalue. Note, a one-dimensional invariant subspace of our linear map T only exists if T has an eigenvalue. Meaning the only way that we can have a 1D invariant subspace of T is for that subspace to basically, when you use T as its map, maps back into a scalar multiple of that particular vector. And that scalar multiple is our eigenvalue, lambda. If that's the case, then we can write TW is equal to lambda W, and we can now pull that to one side and say that T minus lambda I times W is 0. And now we can comment on a particular property of W, meaning thus the eigenvectors of this linear map, which is really a linear operator T, corresponding to these eigenvalues, or this eigenvalue lambda, are in fact in the null space of T minus lambda I. Since T minus lambda I W is equal to 0, if we find a lambda and a W that satisfy that, then W is definitely in the null space of T minus lambda I. And what did we say about null spaces and operators? We know that they're invariant to T, so now we know that this particular vector W is invariant to T minus lambda I. This also means they are a subspace of the original subspace V since the null space of any operator is a subspace of V. Or we can now start thinking, or so now, we can think of an invariant one-dimensional subspace has an invariant direction in our original vector space V. Where now vectors in that direction don't change direction when we operate on them with t upon application of t. Let's look at an example of a possible invariant subspace or a linear map that has invariant subspace. Suppose we have a linear map T that is really just a scaled identity map. So that now I want to see if I can find eigenvalues and eigenvectors associated with this linear map T. So I'm wanting to see, is there a vector W or vectors W associated with T that satisfy TW equals lambda W? Or what happens now if I replace that linear map T with that specific operator, a scaled identity map, AI? What's that identity map do on the left-hand side, or can I actually simplify that left-hand side? I have A times an identity map. So I have A's on the diagonal, if we sort of thought of it in a matrix fashion, relative to this vector W. Is that the same as scaling each coordinate of W by A? Which means that I can get rid of that identity map and I can say, oh, AIW equal lambda I is equivalent to AW is equal to lambda W. So now, no matter what the dimension of T was, or whatever that identity map dimension was, what's my eigenvalue for that linear map? It's only A, isn't it? That's the only eigenvalue that I have. The only eigenvalue for that particular example is lambda equal A. And what are the vectors W that satisfy that relationship? Now I want A times a vector equal lambda times a vector, meaning I want to map a vector W through this identity map and have it equal A times that vector. What vectors will that be true for? Or can you simply put down a quick example and see what kind of vectors that might be true for? Does it really matter? Could be any vector, couldn't it? And any vector is going to then get scaled by A to give us that particular relationship. So this particular identity map scaled by A is true for any vector that we decide to select from our underlying vector space V. Or it's true for all vectors in, or all vectors in V can be thought of as eigenvectors for that particular scaled identity map AI. And that really says that the direction of any vector that we start with, gets left unchanged when all we're doing is scaling it by A. The direction of any vector is left unchanged by application of this linear map T, or linear operator T, equaling AI. Let's look at a second linear map. Suppose that we now have T, and it operates on a 2-vector, W1, W2. And what it does to W1, W2 is it takes the y-coordinate and negates it and puts it in the x position, and it takes the x-coordinate and puts it in the W1 direction. And we've already seen this, haven't we? This is that rotation. And what's going to happen now? Well, let's say that we're given a W that's in F2. So W is now W1, comma, W2. And we now want to see, can we find a lambda, an eigenvalue, and an eigenvector that satisfy this TW equal lambda W relationship, which says that we want TW is actually going to be minus W sub 2 W1. That's what TW is, if W is W1, W2. And we said that that needs to equal, using this eigenvalue eigenvector equation, that needs to equal lambda times the original W, which is W1, W2. So now what do we have? Well, let's look at the two different coordinates to see if we can find some relationship between lambda and W. In the first coordinate, we see that minus W sub 2 is supposed to be a scalar multiple of W1. Or we could solve that for W sub 2, or multiply both sides by minus 1, and we have W2 is minus lambda W1. And looking at the second coordinate, what does that give us? That says W1 is equal to lambda W sub 2. But we can now combine those two, and if we start with W1 from the second coordinate condition, that's equal to lambda W sub 2, but W sub 2, we have an expression for that in terms of lambda, or W1 from the first coordinate. That's now lambda times minus lambda W1, or that's now minus lambda squared W1, and we want this to hold for non-trivial W1s. Obviously, we could make this equation true if we just set W1 equal to 0. That's not what we want, but now what do we have? Well, if we just realize that on the left we really have 1 times W1 equaling minus lambda squared W1, what does that tell us? That now says that minus lambda squared is equal to 1, or lambda squared is equal to minus 1. And is there a real number which when we square it we get a negative? No. So now we are seeing that there's no way that we can find an eigenvalue-eigenvector relationship for a one-dimensional subspace if we're restricted to real eigenvalues. And we'll pick up there and show how we can get, and we've already done this before, but we'll then find imaginary or complex eigenvalues to generate these invariant subspaces that we need.